Okay, so welcome back, and in this lecture I'm going to look at the dual problem that we have derived using so much hard work in the previous two videos and look at what this all means. Okay, so we're going to look at weak and strong duality properties. Okay, so what are we looking at here? So the original problem is henceforth called the primal problem, okay, to contrast it with the dual problem. Okay. And recall, how did we derive the dual? So to derive the dual, we associated multipliers y1 through ym with every constraint in the original problem. Okay, we even associated multipliers with these constraints, but we got rid of them later on. Okay, and we found out that any set of multiplier values that satisfies these constraints, A transpose y greater than equal to C and y greater than equal to 0, gives us a bound of B transpose y on the dual variable. Okay, on the primal objective. So this gives us a bound on the primal objective, and this we minimize to find the most stringent bound on the primal objective. It's actually a very magical, and I'm in awe of the basic idea of forming this dual problem. It's an awesome idea. It's a great idea. Okay, and I'm always shaking my head at how simple and how elegant and how beautiful this whole theory comes out to be. All right. Okay, so we can convert this dual into a standard form. So the dual problem is not in a standard form, and it needs to be converted to a standard form if we are going to use the simplex algorithm that we have already seen to solve the dual. Okay, so if you want to solve the dual, we are going to use the simplex algorithm. But before we go there, let's not worry about this. Let's keep the dual problem as in this form. Okay, and I'm going to call this, for the lack of a better name, I'm going to call this the dual standard form. Okay, we studied the standard form for the primal problem, which is ax less than equal to b, x greater than equal to 0, and this I'm going to keep it as the dual of the standard form. Okay, and let's keep it this way. Let's not worry about solving the dual problem using simplex. Let's first convince ourselves why we should worry about the dual problem. What does the dual problem give us in relation to the primal problem? And you can see it gives us a lot. Okay, let's go for this. Okay, so if you want to compare and contrast the primal and the dual problem, what are we looking at? Well, the primal problem has n variables. Okay, we write them as x1 through xn, and it has m constraints. So A is the m cross n matrix. Okay, and if you look at the dual, that's just reversed. Variables become constraints, constraints become variables. So the dual has m variables, y1 through ym. We use the convention of writing y for dual variables and x for primal variables, and it has n constraints given by A transpose, which is a n cross m matrix. Okay, so that makes sense. All right, so the problem matrix here is A. The problem matrix here is A transpose. Okay, the objective vector is C, and we are maximizing it. Okay, the objective vector is B, and we are minimizing it. Okay, and likewise, the right-hand side of the inequality in the primal problem is a B, whereas the right-hand side is a C. So B and C exchange places. So B and C exchange places. Okay, max changes to a min. Okay, less than equal to changes to a greater than equal to. The only thing that doesn't change, and this confuses a lot of people, is originally we had x greater than equal to 0. Now we have y greater than equal to 0, and that doesn't change. The variables remain non-negative, and for various reasons. This was assumed by fiat, or assumed, okay, by command. We assumed that x was greater than equal to 0, and we need y greater than equal to 0 because the multipliers that we multiplied every inequality with needs to be non-negative, and we saw this 2 videos ago. Okay, so hopefully that's still fresh in your mind, and therefore the multipliers need to be non-negative, or else they change the polarity of the inequality. So therefore we need y greater than equal to 0. Okay, now if all that is very clear, let's look at some properties of the dual in relation to the primal. Okay, so here is the basic theorem, and we call this the weak duality theorem. Okay, weak because there is a stronger version of this that's just coming up. All right, so what does it say? So here is the primal problem, and here is the corresponding dual problem. Okay, what I'm saying is let y be any dual feasible solution. So y satisfies these constraints. It need not be optimal. It just needs to satisfy the dual constraints. Likewise, let x be any primal feasible solution. So x need not be optimal. X just satisfies the primal constraint. Okay, what we are saying is that the objective value that y achieves, it may be suboptimal, but the objective value it achieves is greater than equal to the objective value x achieves. Okay, picture. All right, so here's how the picture looks. So we have the primal objective, and I'm going to call that Z. Okay, the primal objective, I'm going to call it Z. The dual objective, I'm going to call it W. Just as a convention, I'm going to call it W. Okay. Now what we are doing is we want to find the maximum possible value Z star. Okay. And let's say there is some value X which is feasible, which achieves Z, and Z better be equal to C transpose X. Okay. So some value X feasible achieves Z. So Z may be equal to Z star, but in general Z is less than equal to Z star because we are maximizing, so it better be less than equal to. And likewise, looking from the dual world, okay, go back to the previous slide. All right, looking from the dual world, you get the following. Okay, I have, okay, W as the dual variable, dual objective that I'm trying to minimize, and when I minimize it, I'm going to get some value W star, and W star may be equal to Z star. We don't know. We don't know. Okay. All I'm saying is suppose we have some feasible solution Y, which is dual feasible, which satisfies the constraints of dual, and let's say it achieves a value W, which is equal to B transpose Y. Okay. What we are saying is any suboptimal dual solution is going to be greater than or equal to any suboptimal primal solution. It can be optimal or suboptimal. Okay. So any dual solution is going to be greater than or equal to any primal solution. This is very interesting. Okay, let's prove it. The proof is very simple and very nifty. But understanding what we are trying to prove and visualizing it through this picture is very important. Okay, so we have Y, we have X. Okay, so we have Y, we have X. These are given to us. Let's look at this magic quantity. Okay, and I'm going to call it Y transpose AX. Okay, all right. So what am I doing? I'm multiplying. So this is A11 through A1n, AMN, AM1. So this is the matrix A. Okay, and I'm multiplying here by this row vector Y1 through Ym, and I'm multiplying on the right by a column vector X1 through Xn. Okay, why am I doing this? This is just a proof artifact. I'm doing this so that the proof becomes one line as opposed to 5 lines. Okay, but let's do this and then see why maybe. Okay, all right. So if I consider this Y transpose AX, what can I say about it? Well, on one side, we know that AX less than or equal to B. Why do we know that? Well, we know that because X satisfies the constraints for the primal problem. So therefore, we know AX less than or equal to B. So therefore, since every value in Y greater than or equal to 0, since each of these are greater than or equal to 0, I can say that this guy is less than or equal to Y transpose B. Okay, because AX less than or equal to B. Now, if some Y's were negative, you cannot say less than. You cannot say this. This is very important that Y1 through Ym are all greater than or equal to 0. Okay, so this is on one side. On the other side, we know that A transpose Y greater than or equal to C. Why do we know this? Because we know Y satisfies the dual constraints. Okay, and if you want to write it in a different way, transpose both sides. You know Y transpose A, okay, greater than or equal to C transpose. We know that. Okay, and since X is greater than or equal to 0, we can split the summation apart this way. Okay, and so you get Y transpose A, which is greater than or equal to C transpose. So you get C transpose X from this side. So because this is greater than or equal to C transpose, you get C transpose X less than or equal to Y transpose AX. And the reason you can say this again is because X greater than or equal to 0. Okay, therefore we get C transpose X less than or equal to Y transpose AX. Okay, and on the other side we get less than or equal to Y transpose B. And Y transpose B is just the inner product of Y and B, can also be written as B transpose Y. So therefore, you get B transpose Y greater than or equal to C transpose X. Okay, so what have we proved? What we have proved is any dual solution, any dual feasible solution, okay, achieves an objective that's greater than or equal to any primal feasible solution. Okay, now if this theorem is clear, let's move on and show the following obvious fact. Okay, let Y star be an optimal solution for the dual, and let X star be an optimal solution to the primal. Then obviously B transpose Y star greater than or equal to C transpose X star. Okay, and this is just a corollary from the previous lemma. Okay, so that's called weak duality theorem. This is pretty weak. In fact, what we are going to show is the following. In fact, not only they are greater than equal to, they are actually equal. Okay, for a linear program, and this is not true for any other optimization problem. Some optimization problems have it, some optimization problems under some constraints like strongly convex constraints, strongly convex objectives, and so there are some, and with some constraint qualifications you get this. In a linear program you get this naturally, this holds for free, okay, that the dual problem gives you the same objective value as the primal problem. Okay, they are both giving you the same value, which means the best bound that the dual gives you actually coincides with the best value that the primal can give you. Okay. Now here is another useful result. Okay. Let X be any primal feasible solution and Y be any dual feasible solution. This is just a corollary of what we've been talking about so far, such that the objective that Y achieves is the same as the objective that X achieves. So dual objective of Y is the same as the primal objective achieved by X. Okay. If that is the case, then we can say something important. We can say X is actually primal optimal and Y is dual optimal. Okay. Why is that? Well, if it weren't the case, suppose it's not the case, then X achieves some primal objective value Z. Okay, so maybe there is some other function X star that achieves Z star, which is strictly better. Okay, but now look at Y. Y achieves the same value of the dual objective function, which is W. Okay, and what you get is a direct contradiction to weak duality. So if this has to hold, then X is primal optimal and Y is dual optimal. Okay, this is a direct corollary of the theorem that we proved previously. Not very deep, again very simple stuff, but very elegant and very beautiful. Okay, and now we state formally the strong duality. Okay, so what it says is, suppose X star is a primal optimal solution for a linear program. Suppose X star exists and it's primal optimal, then A, the dual problem has an optimal solution. Okay, it cannot be unbounded, it cannot be infeasible. We are coming to that in a second. Okay, and any dual optimal solution Y star satisfies that the objective, the dual objective W star, is equal to the primal best objective Z star. And finally, let's get to the following fact, which is, okay, if the primal problem is unbounded, so far we've been assuming that the problems have optimal solutions. Even if we haven't stated it out aloud, we've been implicitly assuming it. Okay, so we've been assuming that it's feasible, has optimal. So here's the deal. If the primal is unbounded, then the dual is infeasible. Likewise, if the dual is unbounded, then the primal is infeasible. Let's prove this. Okay, we'll prove the reverse direction. So instead of proving this, we are going to prove its contrapositive. So its contrapositive statement says, if dual feasible, then primal is bounded. Okay, why is that? Well, let the dual problem be feasible. Let Y be, so we are proving this first one. The second one is just the reverse argument. Let Y be a feasible solution for dual. Okay, and what we are saying is, let's look at the objective value that Y achieves. So it achieves an objective value. W is B transpose Y. Okay, now immediately we know that the primal is bounded because the objective value Z star that the primal can take is less than or equal to W. Okay, and since Y is a proper number, this is a real number. This is not infinity. Okay, and therefore the primal is bounded. Very simple. Okay, what we are saying is, if the dual is feasible, then the primal is bounded. Alternatively, in the contrapositive, if the primal is unbounded, then the dual is infeasible. Likewise, if the dual is unbounded, then the primal has to be infeasible. Okay, if one of the problems is unbounded, then the other side has to be infeasible. And likewise, if one of the problems is infeasible, then does it mean that the other side is unbounded? That's not clear. Okay, so the implication holds this way. The reverse implication in general doesn't hold, and we will see an example why it doesn't hold. Okay, so here's the picture so far. Okay, so here we are talking about the dual problem. Okay, and here on the top, here we talk about the primal. How do we interpret this? Okay, we interpret this as follows. Okay, suppose the primal has a dual as an optimal solution, and the primal has an optimal solution. That's possible. They can both have an optimal solution at the same time. Okay, and what's impossible is that the dual has an optimal solution and the primal is infeasible. This is impossible. Likewise, this case is impossible. The dual has optimal, primal is unbounded. This is impossible. Likewise, primal as an optimal and dual is unbounded. Impossible, impossible. Both problems cannot be unbounded at the same time. Impossible. If the primal is unbounded, then dual has to be infeasible. If the dual is unbounded, primal has to be infeasible. Okay? But if you go back to the previous slide, I said the reverse implication doesn't hold. And here is why it doesn't hold. It's possible that both of them can be infeasible. So if the primal is infeasible, then you can say either that the dual is infeasible or the dual is unbounded. Okay? But let's give you an example where both problems can be infeasible. And here is the example. Okay? It's not there's no good reasoning behind the example. It just so happens that you can construct it. The primal is infeasible because of this constraint, x1 less than equal to minus 1, which conflicts with x1 greater than equal to 0. Okay? And likewise, the same constraint appears in dual, y2 less than equal to minus 1, which conflicts with y2 greater than equal to 0. So they are both infeasible. And you can check that this is actually the dual of this. So this is primal, and this is dual. You can check that they are kind of primals and duals of each other. Okay, so we are done examining the properties of the dual problem. Okay, so there is one last thing that we'll talk about in terms of the dual problem, which is the notion of a dual certificate. Okay, and we'll do so in the next video. Thank you.